Hello everyone. Today we're looking at minimum string length after balance removals, which was question 2 in a weekly contest for 76. So the question reads that we are given a string S consisting only of the characters A and B. We're allowed to repeatedly remove any substring where the number of A characters is equal to the number of B characters. After each removal, the remaining parts of the string are concatenated together without gaps. What we want to do is return an integer denoting the minimum possible length of the string after performing any number of operations. So essentially what we want to do here is we want to find those substrings where the number of A's and B's are equal. We want to remove those and ideally make the length of the remaining string as short as possible. So looking at the example here, we're given the string AA, BB, AB, and our final output would be 0. And it's 0 because we can actually remove this entire string, right? We see that there's 3 A's, A, and then 3 B's, B, B, B. So this entire substring can be removed and just leave us with nothing, which would be 0. So I'm going to first show a way you might be able to approach this and then explain why it's incorrect and show you how you should actually do this and some things to look out for to let you know to use this certain technique. So let's think about what we want to do. We want to remove substrings where the number of A's and B's are equal. So what if we iterate through the string and at any point, if we find the numbers of A's and B's that we've seen are equal, we can remove that substring, right? And we can reset to 0. So let's go through this example and see what happens. So let's have two variables. We'll have A equals 0. We will have B equals 0. Right, and let's just do that. So we come here, we see an A, make this 1, see another A, make this 2, and now we see a B. Let's make this 1. Let's see a B. We make this 2. All right, so see what happened here. We have 2 A's and 2 B's. So using this technique, we could remove them. Okay, and now we're going to reset these, so these both become 0 now. And let's go through again. So now we have 1A, we have 1B, and again, equal, so let's remove them, right? So now we're left with 0 characters. And you might be thinking, okay, this looks good. This looks like what we want. But let's look at another case to see when this technique would not work. So what if we instead had something like this, A, B, B, right? And you might notice immediately that we can remove this substring right here because there's 2 A's and 2 B's. But if we use this technique, let's see what would happen. So we'll have A equals 0, B equals 0. Let's go through. So I won't go through everything in detail, but let's say we get to 3 A's right here. And then at this point, we start counting the B's. So we get 1, and then we get 2, right? So you'll see that at no point did we ever actually get to a place where the number of A's we counted and B's we counted are equal. Because by the time we got here, we counted 3 A's, but when we count the B's, we never get to 3. So just naively looking for when these counts are equal and removing that substring is not going to be sufficient here. So let's see how we would actually solve this problem. So instead, what we're going to do here is we're going to use a stack. And there's one thing in this problem where if you've seen similar problems, a stack should immediately jump out to you. So remember in the description, it says when we remove parts of the string, remove substrings, the remaining parts are concatenated together. And this is something that you will see quite frequently when we want to use stack problems with strings. So you can imagine that using a stack allows us to remove certain parts of the string. So say we have like a match in the middle. Let's just say we have like some string here, X, Y, Z, Z, Y, X, right? If we say, oh, like we see these 2 characters, we can remove them. Well, we might have these in our stack. And then what we do is we're going to push these onto the stack later, right? So this is essentially allowing us to put these 2 parts of the string together. Even though this was in the middle, right? We used our stack to remove it. And then we are essentially looking at these 2 parts of the string now and combining them. So whenever you see that the strings are going to be combined back together, it's always a good idea to use a stack. So what we want to do here is just maintain a stack of the letters that we've seen. So let's draw out a stack and let's see exactly how this is going to work. So I'm going to just push elements onto my stack. So first I have my A, then I'm going to come to my second A, and then I get to this B. So this is where things get interesting, right? So we kind of have to reframe how we're thinking about the problem, right? We might previously have thought, like, let's try to find the longest substring that we can where all the characters match and remove it. But instead, we want to kind of reframe it as, if we see an A and a B together, well, let's just remove that, right? Because we know that the rest of the strings are going to get pushed together, and we know that we can for sure remove this. So let's kind of greedily remove this case whenever we see it. So what we're going to do is we're going to say, okay, let's push this B on, and then we see that we have a B and an A. So what we're going to do is we're going to remove these both from our stack, right? So now I've removed the B and the A, and I'm going to record the number of removals that I've had. So I've removed 2 characters. So now let's continue going through our string. So now we're going to get to this B and push it on. So same thing here. We have a B and an A next to each other. So let's just remove them. So here, and we can update our removals to 4. So now we're going to continue through. We're going to push our A on. We don't do anything. And then again, we get to this B. We're going to push it on. We see a B, A next to each other. We remove and update our removals. So now we see that we've removed 6 characters, right? So now at the end, what we want to do is just take the length of our string, so the length of S, and minus the removals from it. And this will tell us the final length of the string, the minimum length that we can create. So let's now try the other example that broke our previous algorithm and see how it works in this case. Now let's do the same thing and see what happens here. So we're going to have A, and then when we get to this 4th character, this B, what will happen is that we're going to push that on. And then we see a B and an A next to each other. So we're going to pop these off and we'll record 2 removals. And now you can kind of see in this next case what we mean by that concatenating the parts together. So we get to this last B and we'll see that we can compare this B here with this A down here. And these were not previously together, right? There were 2 characters in between them. But because we've used that stack and we're removing the characters as we see them, it essentially allows us to combine the remaining parts of the string after we remove them and continue those checks. So now again, we see there's a B here and an A here. And again, we can remove these. So we're just going to remove those and have 4 removals. So then at the end, essentially what's going to happen is we'll take the length of our string, length of S, which is 5, and we can minus our removals from it, which is 4, to get 1. And this is correct in this case because we are able to remove this entire section of the string, but there's no way to remove this first A, right? So it does make sense that our final answer would be 1, since the minimum length string that we can create here will always be this 1 character because that A is not matched. So the time complexity here will be O of n, right? Because we are going through the string just 1 time. And when we're doing our stack operations, we're only ever comparing 2 characters at a time. So we're not iterating through the stack or doing anything like that. So it's just a simple O of n time complexity. This base complexity will also be O of n because potentially we could store the entire stack, the entire string in our stack rather, which means we'd be using O of n extra space where n is the size of that string. Let's take a look at the code and see exactly how this works. So the code for this is actually very simple. So we're going to start with our stack data structure and then have this removals variable just to track the number of removals that we have seen so far. So we're going to iterate to the string s, and we're going to append that character onto our stack. So essentially what we're going to do is while we have greater than or equal to 2 characters, right, and we have to have at least 2 to do this comparison, and those 2 characters are not the same. And we don't we don't really compare, like we don't have to check for an A and a B here. We know that we're just going to have these two characters, right? There's the only possibilities. And we know that if they're not the same, the top two at the stack, we don't care which one is which. We just know that we can remove them. So this check is sufficient just to say those characters are not the same. One's an A, one's a B. Let's get rid of them. So we add 2 to our removals, and then we're going to pop off that stack twice just because we're removing 2 characters. Then at the end, we're just going to return the length of the string minus the number of removals that we've done while iterating through the string. So let's submit and make sure that it works. And it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe, and thank you for watching.